Welcome to our deep dive into black hole thermodynamics and its relationship to the fascinating world of quantum information. You're no stranger to the idea that black holes are, well, more than just cosmic vacuum cleaners, but we're going to explore how these objects through the lens of quantum mechanics really challenge our understanding of entropy information and even the nature of space-time itself.
That's right. Our journey begins with Jacob Bekenstein's groundbreaking proposition in the early 1970s. He suggested that black holes possess entropy, a concept typically associated with the disorder or randomness of a system. Now, you might be wondering, how can a black hole, an object seemingly defined by its simplicity, have entropy proportional to its surface area?
Yeah, it is counterintuitive, and it goes against the classical view of black holes as, hairless objects, fully described by their mass, charge, and angular momentum.
Precisely. Bekenstein's insight stemmed from considering what happens when matter falls into a black hole. Imagine you throw a book into a black hole. The book carries information and a certain degree of entropy. Classically, once the book crosses the event horizon, it's gone, seemingly violating the second law of thermodynamics, which states that the total entropy of a closed system can never decrease. To resolve this apparent paradox, Bekenstein argued that the black hole itself must have entropy, and that this entropy must increase by at least the amount carried by the infalling matter.
So the black hole's surface area acts as a measure of its entropy. The larger the black hole, the more information it can potentially absorb without violating the second law of thermodynamics.
Exactly. But it's not just about preventing violations of the second law. Bekenstein's proposal implied that black holes are not the simple featureless objects predicted by classical general relativity. They possess a hidden complexity, a thermodynamic character that hints at a deeper underlying structure.
Okay, then came Stephen Hawking's groundbreaking discovery in 1974. Black holes aren't entirely black. They emit thermal radiation due to quantum effects near the event horizon. This challenged the classical notion that nothing can escape a black hole's gravitational pull. Can you walk us through the mechanism behind Hawking radiation?
Certainly. In quantum field theory, empty space, or what we call the vacuum, is not truly empty. It's teeming with virtual particle-antiparticle pairs that constantly pop in and out of existence, borrowing energy from the vacuum, and then annihilating each other, returning that energy. Now imagine this happening near the event horizon of a black hole. Sometimes one particle of the pair falls into the black hole while the other escapes to infinity.
So the infalling particle carries negative energy, effectively reducing the black hole's mass while the escaping particle becomes real, carrying away positive energy.
Precisely. And since this escaping radiation has a thermal spectrum, meaning it's characterized by a temperature, we arrive at the concept of black hole temperature, directly proportional to the black hole's surface gravity. This implies that black holes not only possess entropy, but also have a finite temperature, a characteristic of thermodynamic systems.
Fascinating. Now this raises an important question. How can a black hole from which nothing can classically escape have a temperature? To understand this seemingly paradoxical notion, we need to delve into the fascinating world of Rindler space and the Unruh effect.
Indeed, Rindler space provides a simplified framework for exploring aspects of black hole physics. Imagine an observer constantly accelerating through flat spacetime. From their perspective, they experience an event horizon beyond which information cannot reach them. This situation is mathematically analogous to an observer hovering near the event horizon of a black hole.
So the accelerating observer is like someone standing on an accelerating rocket, constantly needing to exert force to avoid falling back. They perceive an information horizon behind them, similar to a black hole's event horizon.
Precisely.
Yeah.
And here's where the Unruh effect comes into play. It states that an accelerating observer in a vacuum will perceive a thermal bath of particles as if they were immersed in a heat bath with a temperature proportional to their acceleration.
So just by accelerating, you experience a thermal environment. That seems incredible.
It's a profound consequence of combining quantum field theory with the principles of relativity, and this effect helps us understand the thermal nature of black holes. An observer hovering near a black hole's horizon is constantly accelerating to resist the immense gravitational pull. According to the Unruh effect, this observer will perceive a thermal bath of particles, the Hawking radiation, with a temperature determined by their acceleration, which is related to the black hole's surface gravity.
This establishes a deep connection between the observer's experience of acceleration and the black hole's temperature, providing a framework for understanding how a black hole can emit thermal radiation despite its immense gravity.
Yes, and this is just the beginning. To probe the depths of black hole thermodynamics, we must venture into the realm of Euclidean spacetime. It's a mathematical tool that allows us to explore quantum fields in curved spacetimes in a more manageable way.
Euclidean space-time. Can you elaborate on what that entails?
Yeah.
And why it's relevant to understanding black holes?
Imagine taking the spacetime described by Einstein's theory of general relativity and replacing the time coordinate with an imaginary version of itself. This process is called Wick rotation, and it essentially transforms the geometry of spacetime from a Lorentzian to a Euclidean signature.
So instead of dealing with the usual concept of time, we're working with a time coordinate that has properties of space.
Precisely. And this seemingly abstract trick has profound consequences. When we Euclideanize the Schwarzschild metric, which describes a static, non-rotating black hole, the singularity at the center of the black hole disappears.
That's intriguing. So by switching to Euclidean spacetime, we're smoothing out the most problematic feature of a black hole, the singularity where our current understanding of physics breaks down. What does this imply about the nature of black holes?
This suggests a deep connection between thermodynamics and the geometry of spacetime. In the Euclidean framework, the black hole horizon becomes a smooth surface with no singularity. This allows us to calculate thermodynamic quantities like black hole entropy and temperature, confirming Hawking's results from a different perspective.
It's as if the very fabric of spacetime, when viewed through the lens of Euclidean geometry, reveals a hidden thermodynamic order within the seemingly chaotic environment of a black hole. This is where it gets truly fascinating.
Indeed. And this is just the tip of the iceberg. The connection between black holes, thermodynamics, and quantum information runs much deeper, leading us to the heart of the black hole information paradox and the mind-bending implications for our understanding of the universe. But perhaps we should pause here for now.
Yes, I think we've covered a lot of ground already.
Hmm.
We've gone from Bekenstein's revolutionary entropy proposal to Hawking's thermal radiation and explored the strange connection between acceleration, temperature, and the Unruh effect. We even ventured into the abstract realm of Euclidean spacetime where the black hole singularity seemingly vanishes.
Right, we've established the foundation for understanding black holes as thermodynamic objects with entropy, temperature, and a profound connection to quantum phenomena. But the real mystery, the question that has puzzled physicists for decades, is what happens to the information that falls into a black hole.
This leads us to the heart of the information paradox. Where does that information go? Is it truly lost, or is it somehow encoded in the subtle correlations of the emitted Hawking radiation? We'll continue our deep dive into this captivating territory in the next part of our exploration.
As we continue our exploration of black hole thermodynamics and the puzzle of information, we encounter a powerful theoretical framework that provides profound insights into the relationship between gravity and quantum field theory. The AD-SCFT correspondence.
The AD-SCFT correspondence, that sounds like a rather complex concept. Can you break it down for me?
Certainly. The AD-SCFT correspondence, or duality, postulates a remarkable equivalence between a theory of gravity in a higher dimensional spacetime, known as anti-de Sitter space, and a quantum field theory without gravity residing on its lower dimensional boundary. It's a holographic principle suggesting that the information content of a region of space can be entirely encoded on its boundary.
So you're saying that the complexities of a gravitational theory in a higher dimensional space can be fully captured by a non-gravitational theory on a lower dimensional boundary. It's like a three-dimensional object casting a two-dimensional shadow that somehow contains all the information about the original object.
Precisely. And this duality has profound implications for studying black holes. Anti-de Sitter space, unlike the asymptotically flat spacetime of our universe, acts like a box due to its negative cosmological constant. This means that any radiation emitted within ADS space remains confined, allowing us to study the thermodynamics of black holes in a more controlled environment.
That makes sense. In our universe, a black hole would eventually evaporate completely due to Hawking radiation, making it difficult to study the feed of information in the long run. ADS space provides a more stable setting for these investigations.
Exactly. And one fascinating phenomenon in AD-SCFT is the Hawking-Page phase transition. At low temperatures, the dominant configuration in AD-S space is simply thermal radiation. However, as the temperature increases beyond a critical point, a black hole spontaneously forms.
So it's like a phase transition in thermodynamics, where water changes from liquid to vapor as you increase the temperature. But here, instead of water turning into steam, empty space transitions into a black hole.
Precisely. This phase transition highlights the thermodynamic nature of space-time itself and demonstrates how the eta-CFT correspondence can be used to study non-trivial gravitational phenomena in terms of a dual quantum field theory.
This AD-SCFT duality seems incredibly powerful, but how does it help us address the black hole information paradox? To tackle that, we need to introduce the concept of von Neumann entropy, a quantum mechanical measure of information.
That's right. Von Neumann entropy quantifies the information content of a quantum state. Unlike thermodynamic entropy, which measures the macroscopic disorder of a system, von Neumann entropy captures the finer-grained information encoded in the quantum state itself.
So it's like looking at a system not just from the outside in terms of its macroscopic properties, but peering into its microscopic quantum structure to understand its information content.
Exactly. Now consider the process of black hole formation. A star collapses under its own gravity, forming a black hole. Initially, the collapsing star has a low von Neumann entropy, reflecting the well-defined quantum state of the matter that formed it. However, as the black hole settles down, it reaches a state of equilibrium characterized by a large thermodynamic entropy as determined by the Bekenstein-Hawking formula.
So there's a discrepancy between the initial von Neumann entropy of the collapsing matter and the final thermodynamic entropy of the black hole.
Precisely. And this raises a fundamental issue. Quantum mechanics dictates that the evolution of a system should be unitary, meaning that information is conserved. The apparent loss of information as the black hole forms, reflected in the increase in entropy, seems to violate this fundamental principle. This is the crux of the information paradox.
So where does that information go? Is it truly lost as the black hole forms, or is it somehow encoded in the emitted Hawking radiation?
That's the million-dollar question. One compelling idea is that the missing information is encoded in the entanglement between degrees of freedom inside and outside the black hole's event horizon.
Entanglement. That's that peculiar quantum phenomenon where two particles become linked, their fates intertwined, regardless of the distance separating them, right? How does this relate to the black hole information paradox?
Imagine a virtual particle-antiparticle pair created near the event horizon. One particle falls into the black hole while the other escapes as Hawking radiation. These particles are entangled. The entanglement between these particles contributes to the overall entanglement entropy of the system.
So as more Hawking radiation is emitted, carrying away entangled particles, the black hole's entropy, which is related to the area of its event horizon, increases. But how does this resolve the information paradox? Where is that information stored?
The idea is that the black hole's entropy is not simply a measure of its internal disorder, but rather a reflection of the entanglement entropy between the degrees of freedom inside and outside the horizon. This entanglement encodes the information about the quantum state of the matter that formed the black hole.
So the information isn't lost, but rather encoded in the subtle correlations between the particles inside the black hole and those that have escaped as Hawking radiation. But this raises another puzzle, doesn't it? Classically, the interior of a black hole is causally disconnected from the outside world. How can there be entanglement across this divide?
That's the challenge in reconciling the quantum picture of entanglement with the classical picture of a black hole's event horizon. It points to the need for a quantum theory of gravity to fully understand this connection. Quantum fluctuations of space-time itself might provide a mechanism for entanglement to persist across the horizon.
It's like there's a hidden channel woven into the fabric of space-time that allows entanglement to bridge the gap between the black hole's interior and the outside world. But how can we test this idea? How can we probe the nature of this entanglement and understand how the information is encoded?
To address that, we need to bring in another crucial concept, the Page curve. This theoretical curve describes the expected evolution of the entanglement entropy of Hawking radiation over time.
So how does this Page curve help us understand the information paradox? Does it tell us how the entanglement entropy changes as the black hole evaporates?
Precisely. Hawking's initial calculation, based on a semi-classical approach, suggested that the entanglement entropy of the radiation would steadily increase as the black hole evaporates. This implies that even after the black hole disappears, the radiation would remain entangled, leading to a net loss of information.
That doesn't sound right. If the black hole disappears, shouldn't the entanglement disappear with it?
That's what Don Page, building on the principles of unitarity and quantum information theory, argued. He proposed that the entanglement entropy should initially increase as Hawking radiation is emitted, but then reach a peak and decrease as the black hole shrinks.
So the entanglement entropy goes up, hits a maximum, and then comes back down. What causes this turnaround?
The key insight is that as the black hole evaporates, it eventually becomes small enough that its quantum state can no longer be considered independent of the emitted radiation. The entanglement between the black hole and the radiation starts to decrease, leading to a decrease in the entanglement entropy of the radiation.
So as the black hole shrinks, the information it contains starts to, leak out through the entanglement with the radiation. And this is reflected in the page curve.
Exactly. The page curve ensures that the final entropy of the radiation after the black hole is completely evaporated is zero, implying that the system returns to a pure state with all the information preserved.
So the page curve provides a way to reconcile black hole evaporation with the principles of unitarity and information conservation in quantum mechanics. But how do we actually calculate this curve? And how does it connect to the geometry of space-time and the idea of entanglement entropy as a measure of black hole information?
To answer that, we need to delve into the fascinating world of holographic theories and a remarkable formula known as the Ryu-Takayanagi formula. This formula provides a geometric way to calculate entanglement entropy in holographic theories like AD-SCFT, connecting it to the area of minimal surfaces in the higher dimensional bulk spacetime.
So we're back to the idea of holography, where the information content of a region of space is encoded on its boundary.
Exactly. The Ryu-Takayanagi formula gives us a precise way to calculate this entanglement entropy, and it turns out to be intimately connected to the geometry of the bulk spacetime. Imagine a region on the boundary of 8A space. This region has an associated entanglement entropy, which measures the entanglement between this region and the rest of the boundary.
So we're dividing the boundary of ADS space into two regions, and the entanglement entropy quantifies the quantum correlations between them.
Precisely. Now, according to the Ryu-Takayanagi formula, this entanglement entropy is proportional to the area of a minimal surface in the bulk ADS space that hangs down from the boundary and encloses the chosen boundary region.
It's like measuring the shadow of the entanglement between those boundary regions in the higher dimensional bulk space-time.
That's a great analogy, and this formula has profound implications for understanding how information is encoded and potentially recovered from black holes. It suggests that the entanglement structure of the boundary theory is reflected in the geometry of the bulk spacetime.
So the Ryu-Takayanagi formula provides a concrete link between quantum information on the boundary and the geometry of the bulk. But how does this connect to the page curve and the evolution of entanglement entropy as a black hole evaporates?
To see that, we need to introduce the concept of entanglement wedges, regions of the bulk spacetime associated with specific boundary regions.
So each region on the boundary has its own, territory in the bulk defined by the Ryu-Takayanagi formula.
Exactly. These entanglement wedges play a crucial role in determining what information is accessible to an observer in a given boundary region. And as a black hole evaporates, the entanglement wedges change dynamically, ultimately leading to the evolution described by the page curve.
So the page curve, which describes the evolution of entanglement entropy, is ultimately a consequence of the changing geometry of entanglement wedges in the bulk.
Precisely. It's a remarkable example of how holographic principles, like the Ryu-Takayanagi formula, can be used to understand the intricate interplay between quantum information and gravity in the context of black hole evaporation.
This connection between entropy, entanglement, and the geometry of space-time is truly fascinating. But I must admit, it's a lot to wrap my head around. We've gone from the abstract realm of AD-SCFT to the intricacies of the page curve and the Ryu-Takayanagi formula. Can we pause here to reflect on what we've discussed so far?
Certainly. We've covered a lot of ground, exploring how the AD-SCFT correspondence allows us to study black hole thermodynamics in a more controlled setting. We've delved into the concept of von Neumann entropy and how it highlights the information paradox, challenging our understanding of information conservation in the context of black hole formation and evaporation.
We've also explored the page curve, a theoretical prediction about the evolution of entanglement entropy that suggests information is not lost during black hole evaporation, but rather encoded in the subtle correlations of the outgoing radiation. And we've seen how the Ryu-Takayanagi formula provides a remarkable connection between entanglement entropy and the geometry of spacetime, offering a glimpse into the holographic nature of gravity.
Right, we're beginning to see how these seemingly disparate ideas, black holes, thermodynamics, quantum information, and even the geometry of space-time are interwoven into a rich tapestry that challenges our deepest assumptions about the universe.
And yet, despite all these insights, the story is far from over. There are still open questions, mysteries that continue to puzzle physicists and push the boundaries of our understanding.
Indeed. In the final part of our deep dive, we'll explore some of these open questions, consider alternative perspectives on the information paradox, and contemplate the implications of these ideas for the nature of reality itself.
We've journeyed through the depths of black hole thermodynamics, explored the intricacies of entanglement entropy, and even touched upon the holographic nature of gravity. But as with any profound scientific exploration, our journey has, raised more questions than it has answered.
That's the hallmark of truly exciting science. The realization that the more we learn, the more we uncover the vastness of what we don't yet understand. We've established that black holes are thermodynamic objects with entropy and temperature, and we've grappled with the information paradox, which questions the fate of information that falls into these, enigmatic objects.
Right. The page curve suggests that information is somehow encoded in the subtle correlations of Hawking radiation. But the mechanism behind this encoding, the nitty-gritty details of how information is preserved, remains a mystery.
Precisely, and this is where the real frontier lies. One of the key challenges is understanding how the interior of a black hole, which is, classically disconnected from the outside world, can be entangled with the emitted radiation. This suggests that our understanding of space-time, as described by classical general relativity, might be incomplete.
So we need a quantum theory of gravity to fully grasp the intricate dance between entanglement information and the geometry of space-time in the vicinity of a black hole.
Exactly. And while we don't yet have a complete theory of quantum gravity, there are promising approaches like string theory and loop quantum gravity that offer glimpses into how space-time might be quantized at the Planck scale. These theories suggest that space-time itself could have a granular structure woven from tiny loops or strings, and that these quantum fluctuations might provide the missing link between the black hole's interior and the outside world.
It's fascinating to think that the seemingly smooth fabric of space-time might be a macroscopic illusion, emerging from a more fundamental quantum reality where information and geometry are intertwined in ways we're only, beginning to grasp.
Indeed, and this raises profound questions about the nature of information itself. Is information a fundamental constituent of reality alongside matter and energy? If so, what are its properties and how does it interact with the quantum fields that make up our universe?
These are profound questions. They go beyond the realm of black hole physics and touch upon the foundations of our understanding of the universe. It's almost philosophical in nature.
It is, and that's what makes this field so captivating. It's a convergence of physics, philosophy, and information theory, pushing the boundaries of human knowledge and forcing us to re-examine our deepest assumptions about reality.
Before we conclude our deep dive, I'd like to touch upon one more aspect of black holes that often captures the imagination, the concept of white holes.
White holes are theoretical objects that are essentially the time-reversed counterparts of black holes. While a black hole's event horizon acts as a one-way membrane, allowing things to fall in but nothing to escape, a white hole's horizon would behave in reverse. Nothing can enter a white hole, but things can emerge from it.
So it's like a cosmic fountain spewing out matter and energy. But if nothing can enter a white hole, how could it form in the first place?
That's the key challenge with the concept of white holes. Their formation seems to violate the second law of thermodynamics, which dictates that the entropy of a closed system can never decrease. Imagine a white hole forming from a singularity. This would require an incredibly low entropy state with matter and energy converging in a highly ordered manner to create the white hole.
It's like finding a perfectly arranged deck of cards after a hurricane has swept through a room. It seems highly improbable.
Precisely. And even if a white hole could somehow form, it would likely be incredibly unstable. The slightest perturbation could disrupt the delicate balance required to, maintain its structure.
So while white holes are intriguing theoretical objects, they seem to face significant challenges from both a thermodynamic and a stability perspective.
Right, but their study, even if purely theoretical, pushes us to think more deeply about the nature of time, entropy, and the limits of our current understanding of the universe.
As we conclude our deep dive into the fascinating world of black hole thermodynamics and information, it's clear that we've only just scratched the surface of a profound and mysterious realm. These objects, once thought to be simple and featureless, have revealed themselves to be complex, dynamic, and intimately connected to the deepest principles of quantum mechanics and general relativity.
Indeed. The study of black holes has pushed us to confront the limits of our knowledge and has opened up new avenues of inquiry, from the nature of space-time to the role of information in the fabric of reality. And as we continue to explore these mysteries, who knows what astonishing discoveries await us, challenging our assumptions and reshaping our understanding of the cosmos.
Thank you for joining us on this exhilarating journey. We encourage you to continue pondering these mysteries and to seek out further knowledge in this ever-evolving field. Until next time, keep looking up at the stars, for they hold the secrets to the universe's grandest enigmas.